Ever occur to you how strange gravity actually is?
Strange.
Yeah, I mean, it's holding us to the planet, keeps our coffee from just floating away,
Right.
but we never really think about it.
It really is the invisible force that shapes, well, pretty much everything.
And that's what we're diving into today, the wild world of gravity.
Always a fun one.
We're using excerpts from Feynman's lectures on physics today,
Classic.
and they can get a little dense, just a heads up.
A little bit, yeah, but that's why we're here.
Exactly. Think of us as your Feynman translators.
That's right, breaking it all down.
So from ancient astronomers puzzled by the night sky to Kepler figuring out planetary motion.
Of course, we'll get to Newton.
Had to have Newton.
Apple.
But let's start with Kepler. Now, Kepler didn't just magically have all the answers. He used Tycho Brahe's data.
Ah, brah. Years and years of meticulous planetary observation.
Yeah, the OG cosmic data analyst.
Precisely. Provided the raw materials. But it was Kepler who saw the patterns.
And what patterns?
Indeed.
He came up with his 3 laws of planetary motion, and it changed how we understood the entire cosmos.
Revolutionized things, really.
His first law: planets don't orbit in perfect circles.
Nope.
They move in ellipses, like a stretched out circle.
You can picture it, right?
Yeah.
Imagine you have a string and you're drawing a circle, but someone tugs the string a bit to the side as you draw.
Ah, okay.
That's your ellipse.
So everyone thought perfect circles, up until Kepler.
Seems so long ago now.
It's a huge shift. Makes you wonder what other truths we believe now that'll turn out to be wrong.
You never know what the future holds in terms of scientific discovery.
Okay, but ellipses, got it. So on to the second law. What's that about?
Speed. It's all about speed. Planets don't move at the same speed throughout their orbit.
Really? I
Yeah.
just assumed, constant speed going round and round.
Nope. They speed up closer to the sun, then slow down as they move further away. Think of those spinning carnival rides.
Oh, the ones where you get flung outward.
Exactly. The faster it spins, the stronger the outward force.
So planets are basically on a cosmic merry-go-round.
In a way, yes. Closer to the sun, stronger gravitational pull, faster movement.
Makes sense.
But here's the thing. Even with the speed changes, the area the planet covers in its path over a set time, like a week, always stays the same.
Wait, what? How does that even work?
It's like, imagine a slice of pizza, right? No matter where the planet is in its orbit, the area of that pizza slice from the sun to the planet, traced over a week, is constant.
That's wild.
Yeah.
So we've got planets in ellipses, speeding up, slowing down, but keeping their cosmic pizza slice the same size.
It's pretty elegant when you think about it.
Very elegant. But then where does the third law fit into all of this?
The third law, that's where we connect a planet's year, the time to orbit the sun, to its orbit size. Further out, longer trip around the sun.
Okay, so it's like a relationship then, between the year and the orbit.
Exactly. And it's predictable. It's a law, after all. There's a pattern.
So Kepler gave us the how. We know how planets move in this cosmic dance, but the big question is why? Why this way?
And that is where our friend Isaac Newton comes in.
With maybe a little help from an apple.
Perhaps. Ah, the apple. Whether or not it actually hit him on the head,
Right.
it captures the essence of Newton's genius.
It does. So how does a falling apple turn into explaining the motion of planets millions of miles away?
He thought, what if that same force, gravity, what if that's what's keeping the moon in orbit around us?
That's a pretty big leap.
Radical idea, but he was right. So he comes up with the law of universal gravitation.
Universal, huh? Does it apply to my coffee cup too?
Absolutely. It says, every object in the universe attracts every other object. That's gravity.
So what, I'm pulling on you right now, gravitationally.
You are, and I'm pulling on you.
Not enough to notice though, huh?
Not quite. The strength depends on two things. Mass and distance.
Right. The bigger something
The
is,
stronger the pull. So the sun, being the biggest thing in our solar system.
exerts a lot of pull.
Exactly. And then closer objects.
Stronger attraction like magnets.
Perfect analogy. You got it.
But hold on, if it's about mass and distance, how does that actually keep a planet in orbit? It's not like a string tying Earth to the sun.
Exactly. Okay, picture this. Ball on a string. You're swinging it around. That string is providing an inward pull.
To keep it from flying off.
Yeah.
Centripetal force, right. I remember that from somewhere.
That's it. So gravity, it acts like that inward pull for planets. The sun's gravity keeps them from going in a straight line. That's the orbit.
So gravity's like this invisible tether holding everything together.
In a nutshell.
Now, Feynman mentioned something about Newton and the moon. He doubted his own law at first.
Yeah, he needed to know how far the moon falls towards Earth each second.
Falls. But it's not really falling, right?
Right. Not crashing down, but deviating from a straight path because of Earth's pull.
Okay, I get it.
But he was using some bad data about the moon's distance.
Oh, no?
It messed up his calculations at first. It really bugged him for years.
I can imagine.
But once he got better data, everything matched up.
The numbers all made sense.
Exactly. Supported his law beautifully.
Even geniuses got to double-check their work.
It happens to the best of us.
So, besides the moon orbiting Earth, what else did this law help explain? Did it predict anything else astronomers could actually test?
Oh, absolutely. It's not just a cool idea, it's powerful. For example, tides. Why the sea level rises and falls.
Okay, yeah, always wondered about that. Why 2 high tides a day, though? Why not just one?
Because of how the Earth, the moon, and the sun, their gravities all interact.
Wait, the sun, too? I thought this was mainly a moon thing.
It plays a role, but think about the Earth and the moon first. The moon pulls more strongly on the water on the side of Earth closest to it.
Okay, so that makes sense. That side bulges out, high tide.
Right. But here's the thing. It's not just pulling on the water, it's pulling on the Earth itself, too.
Oh, right, I forget. The Earth is moving, too, in all this.
Exactly. And the Earth's center is farther from the moon than that close-up water. So the water on the far side, it experiences less of a pull toward the moon than the Earth's center does.
Whoa, wait, so it's like a difference in how strongly they're each being pulled.
Exactly. And that difference makes the water on the far side bulge out too, second high tide.
That's wild. So the moon's playing tug-of-war with our oceans.
Pretty much. And it's all explainable with gravity.
I love when we can explain those everyday things. What else? You said there were other mysteries Newton cracked with this.
Oh yeah, like why is the Earth round? Why are planets generally spherical?
It's because of gravity, not just because that's a nice shape.
Gravity's the sculptor. It pulls equally from all directions towards the center of a massive object. Over time, that shapes things into a sphere, most stable form.
So a cube-shaped planet wouldn't last too long, huh?
Not if gravity has anything to say about it. And get this, Newton's law. It even helped us find a whole new planet.
What? Seriously? How do you even find a planet with just, like, an equation? A whole planet just hiding out there, messing with another planet's orbit enough that we could say, aha, gotta be gravity, gotta be something there.
It's like its gravity was leaving a fingerprint, even though we couldn't see the planet itself yet. Amazing, right?
That's a great way to put it, a gravitational fingerprint. So it's not just about planets orbiting the sun. This law works on way bigger scales.
Oh, absolutely. We're talking galaxies, those giant collections of stars.
Right, right. Everyone's seen those amazing pictures, but
Gravity is what holds them together. Billions, trillions of stars, all pulling on each other.
so galaxies are like giant gravity playgrounds.
You could say that. And it gets bigger, like stars forming galaxies. Galaxies themselves, they clump together too.
Because of gravity, right. We're on, what, galaxy clusters now? This is getting huge.
Exactly. Galaxy clusters, largest known gravitationally bound structures in the universe.
It's like gravity's this master architect, but working on a scale that's almost impossible to imagine.
And there's more. Feynman talks about how gravity might even be behind how stars themselves form. Those twinkling points of light we see at night.
Yeah. You're going to say it's gravity again, aren't you?
Had to be. It starts with a cloud of gas and dust just floating around. And over, well, a really long time.
Like longer than humans have existed kind of time.
Much, much longer. But those tiny particles, they have a little gravity too, right? So they pull on each other, they clump up.
Okay, and then those clumps, they pull in even more gas and dust.
Exactly, because they're getting bigger, stronger gravity. It snowballs.
Cosmic snowball fight. And eventually, boom, a star.
The clump gets so massive, so much pressure inside, nuclear fusion ignites.
A star is born, but we can actually see this happening, like through telescopes.
It's tough. They're far away, forming slowly. But Feynman describes these images, taken a few years apart.
Yeah. What do they show?
A region of gas, and then new bright spots have appeared.
Baby stars. I love it. But as cool as all this is, Feynman also points out the stuff we still don't get about gravity.
Right. It's like, we've got this map, we can describe how it works, it's predictable.
But we don't know why it works that way.
Exactly. We can say mass attracts mass, but what's the mechanism? That's the mystery.
And then Einstein had to come shake things up even more. Right. With relativity.
Einstein showed us that gravity isn't just this force acting through space, it's a warp in space-time itself.
My brain hurts just thinking about it sometimes.
It's a lot, but it was a huge shift in our understanding. Newton wasn't wrong, he just didn't have the whole picture.
Makes you wonder what the next big shift will be, doesn't it?
Exactly. And Feynman leaves us with this question, something to ponder.
Hit me with it. What's the big question?
What if gravity isn't constant? What if its strength, what if that changes over time?
By changing universe. Maybe, wow. Okay, yeah, I'm going to need to think about that one. A lot to unpack there.
It's a lot to unpack, but that's what makes this stuff so fascinating, right? Always more to learn.
Absolutely. This has been an incredible journey exploring the universe, all thanks to gravity.
Always a pleasure to dive into these topics.
And thanks to everyone listening for coming along on this deep dive with us.